joined for MS and then converted to PhD at IIT Madras. After PhD, I have made two postdocs, University of British Columbia, Canada, NTU, Singapore, and then immediately I have joined as a assistant professor at IIT Tirupati. Currently, I am working as an associate professor. Coming to this today's topic outline, first I will show you that how computers are evolving, our history. All of it is about recent, not about the previous. And then I will look into that there is a new domain where my PhD quantum dot cellular architecture after memory computing. And we are saying acid design for evidence afterward. And then quantum computer only brief. I am not working in that area. There is one secure communication protocol where I have worked. And then we created a demo at IIT Tirupati. I will explain it. Thanks. You can see that first person, what we call Charles Babbage, he is the father of modern computer. After that, you can see that after we can go like a Gilbert type microprocessor. Up to that, you can see some few people which I have mentioned. They are people like very, very experts in their domain. Let's go and see what are the how it went. Next. You see that the first calculator, it looks like it is a mechanical one. And what happened is, you know, when it is, that is the year where Euro commerce throughout the world. So to commerce that they have to travel to the different countries. So when they travel to different countries, they used to take the map, they used to create maps. And that maps, what exactly happening is, you want to remember a route or something coordinates you want to get somehow, you want to know certain things. They are creating a differential equation. To create this differential equation, you have to do a lot of mathematics, and then there's a break some God give you something which will go automatically all this calculation. That is how the God came. Then the God he got, then he created a computer. And it will play the video is below. Next slide. Here below, click on the display. Will not play that. Not play. Below. No, not play. Maybe the YouTube link is available. The damage link. You can see that weight is like a 10,000 pounds. Okay, I mean almost 4,500 kilograms or something. Then what happened is, that is what they are using, like using a difference equation. They created a multiplication, certain addition operations they started doing. And later what happened is, John and Arthur and Clifford Berry, they created a electronic computer using the vacuum tubes. So before inventing of PCID, people are relying on the vacuum tubes. And what is the funny thing about using a vacuum tube? Usually we will do decimal number system, addition, subtraction, everything. When they try to create a decimal based arithmetic operation, they started facing a problem. They are not able to do that. The reason is, you want to create a decimal number system, you have to give it 10 states. Let's assume a signal, in the voltage, you consider 0 is like a logic 0, 1 as a logic 1. If you want to create a 10, 0 to 9 values, it requires how many states? 10 states with it. That's very, very difficult to perform, but he got idea that instead of a decimal, why can't we use it binary logic change, logic one? That idea changed entire history. You can remember which year this is? 1936 or something. Okay. Okay, next. And after that, so this is the ABC mission they built. What happened is this person in the Iowa State University, he built a computer. After he retired, he went to the home and then he is peacefully doing, but they never understand the importance of the computer. Whatever logic he created, he never understand, and then he never made money out of this system. Even though he is the first one to use the Boolean logic, people will call like the area, but before that, the patent was has happened. You know, when he is retired and he is working at his home, suddenly attorney his boss used to go and meet him. And then they have understood that this is the first computer, that's what they have called ABC computer. And this is the area. People, if you remember anything, computer means area. So first electronic computer or what they used to do that one. It is in 1942 or something. That is the year they have been. This is the computer, which is based on a Boolean logic. Okay, whatever people are feeling bored about Boolean logic and what you call switching theory and logic theory, that is the subject. That is what creating all this. Without that logic, you cannot create anything. And so this is the one of the computer. Can you go next? And you can see that 1946 they built 2 lakh man hours. 2 lakh man hours. Let's assume that one day want to work like 2 lakh hours. How many years it take? That meant man hours, and it took like $500 million USD dollars in 1946. Now you can do a compound interest of like at least 8% to 10%. You can understand how much money they spent on that first electronic computer. And the clock frequency, I think it is only 100 kilohertz. And to do a addition, it will only require 100 kilohertz, 1 by 100. This is the time difference. Very, very slow computer. It used to be like very, very big. Maybe 2 to 3 rooms it used to occupy. This is the one of the milestones which happened in the history. The next. So previously people are computers. Why do you think computers are big? What is the reason? Can any of you tell me? What was the reason why computers are very big? Can any of you tell me? Vacuum tubes. Excellent. So this vacuum tubes, let's say you can replace with vacuum tubes with same property. Then they started doing the research. So what happened is, I think there is some sentence is missing. But he doing a job. At the side he started working. Okay, he is getting paid for the job, but on his own request, when he has a time, weekends, he used to go to the lab and he used to work. Finally, they have created a BJT, bipolar junction transistor, and then they got a Nobel Prize because of, we can see these 3 people. So this is the way the entire human history changed. See, you already have Boolean logic. Only device is missing. That device is BJT, and we got a device which can go to nowhere else. Then people started using it. Instead of vacuum tubes, they started using a BJT, bipolar junction system. We can say that from here completely different system. And there is one more very, very bizarre, like there are 2 different people, Sharp India and Robert Policy. They are 2 different companies, 2 different people. Their thought is BJT is based on semiconductors. Okay. What is a BJT? Bipolar junction transistor or diode is based on semiconductors. And you want to create any circuit or something, we need a resistor, capacitor, or inductor. In electronics, mainly we use resistor and capacitor for our computational purpose. We don't use the inductor. Maybe R or something, they will use the inductor in our case. So he got idea. Why can't the same silicon material? Why can't we make a same circuit? Why can't we make a resistor? Why can't we make a capacitor? The thought process of change, and then what they did is, if you do that one, then along with BJT, the same IC is the same place. We can even keep a resistor, we can even keep a capacitor, both of this. And that is the like a mind blowing idea. People have the idea, and nobody achieved, and Jack Gilbey he achieved from a different company, and also Robert Noyce also after, and then they have happened a clash between the two people. Who has to get the patent? Then they went to court, and then it has been so many years that happened. Can you tell me how did two people end up getting the same idea? Can any of you tell me? So this thought is there, everybody has, but what happens is they will go to different conferences. Different people publish journals, they will read like small, they will get an idea in their brains. By reading, by attending different conferences, they will small, they form. And like that, they both got the same idea, they propagated a IC. So finally what happened, both the companies got the patent for integrated circuits. And from this onwards, whatever low size, we can see that entire IC is full of only transistors. And this is the 1960 emitter coupled logic first integrated circuits, which is made by Motorola. And you can see that after that 1990s, Intel 4004, they created a microprocessor. This is very powerful microprocessor at that time. And this is the operating frequency. Previously I told you 100 kHz of the vacuum. Correct. One clock frequency. Means one clock it will take addition. But this is very powerful. You go and check the architecture of this one. And this is the how it looks like a first integrated circuit based for Intel microprocessor 1971, and it contains 1000 transistors. And the operating frequency is 1 MHz. And do you know what is the current operating frequency of our computers? 2 to 3 GHz. We didn't achieve much in the top frequency, but we have achieved more in the volumes. Then that is the up to that point is one. When MOSFET has introduced, what happened is, and you see here, this is the MOSFET. The L is the channel. And what is this circuit? When I have a paper, I have reached a paper, that channel length to reduce the biggest problem using BJT threshold voltage. You cannot change your BJT threshold voltage. But in case of MOSFET, when you change the length, the threshold voltage changes. And by changing the threshold voltage, you can change the operating voltage. If you change the operating voltage without compromising a clock frequency, actually you can reduce the power dissipation. All these advances happened until 2015 or something because of reduction in the channel. And you can see here, after 2015, means 32 nanometer is the last MOSFET. After 32 nanometer, they want to make 28 they made. Below after the 30 nanometer, like after 28 nanometer, is the last MOSFET which is called as. They are no longer using a MOSFET. Because what happens is, when you make this channel small, that is started, if you use small voltage, you are not able to control because of the tunneling effect, that electrons are moving from source to the free line. If you are not able to control it, then people have started going for FinFET. Because FinFET has recently reached the limitation. Now they are going to GAFET, gate all around FET. Intel recently 2 nanometer, 1.8 nanometer FETs are based on the GAFET, gate all around FETs. It all depends upon the channel length. And you can see that you can see that 1971 or something is we got 404. But modern computer, you can see that multi-core and all these things are. And we are in a very advanced stage. That's what we think, but we are not in that much advanced stage. And you can see that previously, you remember that we have only few 3 to 4 cores are there in CPU, but this is the guy from like NVIDIA. 1998 they made a GPU. So what happens is, if somebody doing some applications on graphics, like a graphics card, like a our displays, playing games, we have to frequently upgrade the frame buffer, the display buffer or something, which we need to update very frequently. And the biggest problem about our displays are very huge pixels. Can any of you tell me how displays works? All of you are having your phone, that's correct. It's mobiles. How display works? Very simple. Can you tell me? Huh? You fingerprint it mobiles. Huh? Can any of you tell me how display works? Any idea? LED or LCD? Which is that? LED. What is the LED? Light emitting diode. That's all. Light emitting diode, which is a voltage controlled light emitting diode that contains 3 diodes. You take any pixel in the screen or something on mobile, it contains 3 diodes which is packed in RGB color code. Red, green, blue. And each one, if you apply a proper voltage, 3 channels you have to apply, then it will display corresponding color. That is how our displays work. The biggest problem is the screen size is number of pixels are more, the frame of size is very big, and you have to operate it. And by the way, displays how they will work. Any of you know or not? First, it will display the first row. Next, it will display the second row. Next, it will display the third row. It won't display entire. It will display the first row, second row, third row. But that's why refresh rate of the display is very important. Maybe you have this course called TVs and all these things there, but we have that course. How that TV works, similar manner. So the display is bigger, you have updated frame buffer. The load is more and it is slower. What GPU people come up with? Why do you want to use a CPU? Instead of that, you create a GPU. GPU is nothing but a single instruction, multiple data, in which that will update a frame buffer for display. So initially they started using for games. Main purpose is games. So they started using for games. Then I think Intel has a chance to buy NVIDIA. They have missed that opportunity. Now they are very big. And Intel also started making GPUs, not like generally integrated kind of thing. And what happens is, now NVIDIA started losing a market share. That time came one application. That application is nothing but a blockchain. You know, Bitcoin, Ethereum, there are something cryptocurrencies. They came to create cryptocurrencies or something. They use the concept called mining. So that time they found that which is a high speed for mining is GPUs. Then they made a lot of money. After that, 2014 onwards, these actual GPUs are based on matrix multiplication. When AI came into picture, neural networks, then GPUs, they started using the GPUs for training. That's how NVIDIA gained lot of market. Okay, let me ask you, there was an interview by NVIDIA CEO. He gave that, why can't everybody make their own GPUs? Let's say I want to train any application like ChatGPT. They are spending a lot of billions of dollars. Why can't they make their own chips? Can any of you answer? ChatGPT, they are spending a lot of money, correct? DeepSeek, there is one more company recently. Google Gemini, why can't they make their own GPUs? Can any of you tell me? Yes. To make a single GPU, it will comes around as low as $100 billion it will cost. Let's say you made a GPU, you want to update it again, you have to spend a lot of money. That much amount of money you have to spend. Let's say today you want to make a GPU, it will take how many years? 6 years to get even first GPU. If I start from today, after 6 years or 5 years only I can get my first GPU, which is test. It's very, very complex. That's why people, they don't make their own GPU. This GPU architecture is if there is no make in their GPU, did you ever see any make in their GPU? Because of high fabrication cost, high cost. Unless until government of India supports, you cannot make our own GPUs. Even about India, China itself, they don't have their own GPUs. They say AMD, but AMD is not actually there. That is that much difficult to make any commercial GPUs. And what happened is, why you go for GPU in AI training, for example, I have only single instruction. I can do this CPU. The LKS, the GPU, the matrix multiplication can do very fast. It's a single instruction and multiple. And this all what is matrix multiplication. How fast you do, that much fast I can train my GPU. And there is one thing, actually what they have done is, matrix multiplications are GPU work. But if you go see deep neural network architecture, it contains more matrix multiplication, but activation function, there is a max, there is one more vector multiplication. So what Google people thought, why can't we make our own chip? They didn't call this as GPU or CPU. They made a generic application specific chip that is called TPU, tensor processing unit. The TPU, what it will do is, one of the main one is multiplication. Okay, it is 96 by 96 again, but recently 256 or 256 matrix multiplication will do, and the activation function, and then pooling. They are going to buffer. This is the one of the ideas they got. They fabricated Google. Now they call it as TPU. If somebody want to work or somebody want to pay some money to work on the TPU, okay, it's called neural processing. So if you see that neural processing unit, if you see peak performance, 600 gigaflops means here floating point operations per second, which peak that can compare GPU will do 600 giga. Giga means here 10 power 9 operations which you can do like a GPU. In case of NPU, you can do 18.43 tensor point operations. Okay, so sorry, trillion operations per second. T means trillion, and it is in 8. Basic is integer 8 operation. This will do floating point 32 or 64. So that is why your basics are very important. You see here, wherever you go, whatever are the floating point operations, integer operations, like that will be. And since all of the students, when somebody comes for like a master's or PhD with you, which question do you think we will ask first? Let's say we are address for AI or process. What is the first question we think I will ask? Frequency. See, simple integration, what we will ask is, we will give one positive number and negative number, convert that into a 2's complement format, add those two numbers and plus. If that guy did well, then I will ask him how to create a equivalence circuit. What is the equivalence? You know, almost 90, whoever answers that question, 100 or 99% of the people, I mean 100% till now, they told that whatever modes on the first page, or you get a overflow, then convert to again to 2's complement format or something, you get a correct answer. And then I will ask them how to create a circuit. They don't answer. So arithmetic circuits is the heart of any AI process or anything you want to build your own thing. Arithmetic operations is what first I will ask the question. Where many people they don't answer that addition and subtraction. We don't ask very high level concepts like how do you build a GPU or like that. We will ask simple basics. Like what is the difference between the floating point 32 bit and what is the difference between the integer 8. So these are the basics. You have to start from the basics. Then you should go for very high level. And you know, this is the one of the linear architecture. This is the first neural network, or deep neural network, which is proposed and shows that we can perform a recognition using this network. It took like 1996 or sometime they have used this network. And here all these things are like very see how many number of operations it press, you know. If you have time or something lunch time, you won't take linear. Okay? Linear architecture. How many weights it will have? You try to calculate. You want to recognize training and all this. Okay. So this is the first. You see that even my students, I gave this project. 6 months, 3 to 6 months, I asked him to implement the AI hardware. He is not able to implement it because it is that much difficult level to implement in this hardware. So this is where we have a lot of scope for doing a jobs from research and design. Or you can even create new architectures. Click on this. Next slide. Click on this. Play video. Actually, this is the one of YouTube videos which you got. Usually, GPUs and all these things are used for inference, for application. But training, we need very, you know, at IIT Tirupati, to train any application or something, we bought I think some GPUs, which costed around 2 crores. that is many people can use it, but to try big application, that money is not even enough. You have to go to 100 or 1000 crores to try very big thing to get in a reasonable amount. That much money is required, but what you can do is if somebody wants to buy some free websites or some, they will give provide this training for us. You can do this. And this is the Google True block diagram, and they have created this TPU, tensor processing unit, and you can see here majority is like a buffer, which is a equation, and that is multiplication accumulated. So do you know any of you did any of you implemented harder matrix multiplication? Any of you the hardware to do any matrix multiplication? One of the complex operation is matrix multiplication. Even more complex is matrix inversion. You want to do in a matrix inversion in a hardware, you see the page. Not even that much. You know about all of your EC students. You know Fourier transform. Fourier transform, that fast Fourier transform. 16-point Fourier transform implement in a right HDL code for that, a proper create a multiplication, addition, and try to connect it with parallel with that. You understand how difficult it is. So this is the high level architecture. This is you can somebody want to work on architecture, chip architecture or something. That is very interesting. You have to go to good groups where they are working for this kind of architecture. If you ask me to do your work, I need to work and plan it because you have to compete with big things. You do get a single architecture. When we reached here in 2010 or something, people thought that MOSFET we are not longer able to use it MOSFET. So we have to look for new kind of technologies. Then people started looking into different technologies. Among them is quantum dot cellular atomic. So here the thing is, these are all called quantum dots. Let's assume that we have only 2 electrons. In general, let's say if I place two electrons, which direction they will sit in? This direction or this direction? The reason is the differential, electronic differential is whichever is lower, that is the state they try to stay. Similarly, from that one direction we call it as 1, other direction we call it as 0. And when I joined for PhD, my professor is reading this paper, and I felt very interesting, like quantum or something, talks on the like electronic differential. For example, this is a logic wire. So how it will work is it won't flow any charge or anything. It will only use the force. If you place two electrons side by side, they will repel each other, then they will try to stay in the diagonal. That's how minimum differential uses. This is a technology. And then what happens is the basic gate here is not the NAND gate or NOR gate. Basic gate is majority. So it's a basic gate is majority gate. Majority gate is nothing but a voter AB plus DC plus AC. Since we don't have fabrication facilities there, so I started working theoretical level. Let's assume that instead of a AND gate or OR gate, I will give you majority. How will you create a circuits like added, subtract, divided circuit with less number of majority gates? That was the topic which I have taken, and then I have published on it. This is not. This is not. See, usually we have like two states, 0 and 1. So this is a QC wire operation. So that's how usually it looks like a travel, correct? It is not actually travel, it's a function. Let's say I have initially logic 1 is there. If I provide a logic 0, what will happen? You see. Go on, sir. Back. Slowness. No, next slide. Full content. Let's say apply a input as 0, so they will try to change the position. Now we will get a output 0. See, you see that here there is no flow of electrons. Only the state of electron is changing. This is the quantum dot. The biggest problem about this quantum dot operating at room temperature. Very, very difficult. So that is how we do to say wire operation. And let me tell you why wire is very important. Nowadays, you know, wire is the biggest drawback for any ICs. Wires are the one usually difficult to place. Okay. Previously, when there is 65 nanometer above, wires we never used to consider that much difficult. Below the 65 nanometer, wires is placed lot of role. If you don't reduce wire delay, the circuit is not. So usually inverter operation like this. Is the majority gate. So here one more, so you will get output as 1. This is called majority gate. So this is the first result. When I am discussing with my professor, I got this result. Very, very simple result. Why I am telling? Many of the students think research means building big no. Research fundamental research is looking at small things where the gaps are there. That is where we will try to build it. And all of you know that Elon Musk will come and do the building grid. Correct? And similarly, the GPU person will come and tell that we have made a very great. But if you don't see the teams are something, they are working with very, very low levels, very, very small levels. Sometimes only the one atom will produce a lot of delay to reduce the people has to struggle. So don't fool by like Elon Musk. He don't even build his own atoms. He don't know what exactly inside the atoms. But he knows how to present very nice. Okay. And can you tell me, Elon Musk himself can build an autonomous car? No. He funded money, but the way he understands presence is somewhat that's so don't fool with that you want to build like that. That is the ambition is good, but you have to start from the low level. In case of engineering, you have too much money, you can go and give money, somebody will build for you. That is a difference. So this result, whatever you got, I found that existing 1 bit ladder, ultimately full ladder for your terminology, I found that this repetition I found in 2 places. This is the same and this output also same. I have replaced with the circuit. Then what I have achieved is, you have a 1 bit adder and a full adder. This takes 3 majority gates and 2 adders. And whatever circuit I have built, it will only take single inverter. I have, let's say you have 64-bit data, it will require 64 inverters. And recently, I thought this is not a greater, but whichever papers I am seeing, they are referring to circuit diagram. They are only using, nowadays, they are not using this. 1 inverter, my circuit, whatever I have proposed, this is only they are using the many of the places. So this is the level I have found, very, very low level. So what I am telling is, though fashion is good, for example, I became a faculty now. Now I want to work, I can do to my students work on this area. But when you want starting, you want to start from whatever your professor is. And all of you won't carry looking adder or buy triple carry. Correct. There is one more adder, parallel adders. Many of the computer uses this adder. This is called prefix adder, which is based on prefix operator and associative operator. You wanted to compute like carries or something. Okay. We will compute using this kind of structure. So the problem is, what we do is, can you go here, I have taken the 3 major tickets it takes to compute this prefix operator. And why can't we compute this in 2 major tickets? When you know when I got this idea, 2009 I got this idea. I want to generate a prefix adder. Prefix adder, the prefix operator with only 2 major tickets. That is my goal. So then what I have done is, I started working on it. So what we have done, only in the first layer, I am able to reduce to 2 major tickets. I start taking 3 major tickets. Always, the prefix operator. But what happens is there any possibility to enter my PhD, I got very, very small result, not up to the whatever I thought. Okay? Whatever, but I got a PhD degree with these things. This is the different types of prefix adders. I'm not going to details, but if you create a new adder or something, they will name you. Okay, one of the papers they named my name also. Okay, Boni and Sridhar adder or something like that they name. So if you create different adders, your name also they will. So this is the existing prefix operator. And then when I joined at NTU, there is a paper I was reading, there I got something. Actually, this prefix operator, whatever it is there, we can reduce to 2 major tickets, but you cannot use this formula. You have to use a different formula, then only it is formed. So this is the my prefix operator. So this actually takes A and B, A, J, B, J, and it gives 2 major tickets. They have been decided. So if somebody wants to use major ticket based deep prefix adder, they have to use this operator. You cannot go beyond. So that's how I have created a major ticket based prefix operator, completely redefined. So I got this idea in 2010 when this paper got published. Is 2006. Got completed in 2016. So it took almost like 6 to 7 years. Since I am lucky, it took only 3 to 5 years. If you are not lucky, I could have worked a decade. Maybe in my lifetime I will not have done this. Okay. So don't think small things are not important. Okay. Don't fashion it with A and don't run off. Okay, even small things, whatever you learn in your class is more important than in. Okay? So this is how I have prepared a proper prefix operator entirely. It actually reduces a area by 50%, area by 33%. So this is the layout of that. We always will provide a layouts. It is how you do the layout. QC are no longer working because it is somewhat saturated. Then one of the PhD students joined. I started looking into there's something called in-memory. All of you know about in-memory computing. In you heard about in-memory computing. Current architecture, do you have any idea? Usually we have the RAM. From the RAM, the data will go through the processor. And it will compute again to store into a RAM. So in-memory computing means even the computation will do in a memory. That is called in-memory. We don't transfer to the some place. Where what we will do, the memory itself will compute. We don't transfer. It's actually transferring memory to processing that is called beyond human bottleneck. So where this exactly came is there is a missing fourth element. Somebody found out that there should be one more element between the charge and the flux. Okay. So this is the missing fourth memory star. And this memory star has some interesting properties. It can be used as a memory element. See, none of them have the memory power. Okay. Capacitor, resistor, inductor has some memory, but it is not complete memory. Actually, over a period of time, 20K, but memory star is not. It can store the values, and as well as it can use the computer. So you can see that usually we will have higher resistance state and low resistance state. So that is what we use for computing. 0 is like low resistance, HRS is like higher resistance state. Okay. So this is how we will arrange a memory star followed by a MOSFET. Why do we use these switching capabilities are actually for memory star very good. But the problem is leakage possibility. To avoid a leakage pass, we will arrange like a memory star in a manner like this. So I will load the values. When I load the values, if I read three values together, I will get a majority data. So this is a 1T, 1 or 7, that's about that. So we will arrange all these things like this, crossbar arrays or something. So you load three values, and then I will try to read three values from. To read, you get the three values that will act as like a majority. So I did my PhD majority gate, since it is also majority gate. Then I started working on in-memory computing architecture. What happened? We published some papers. The biggest problem about this in-memory computing, the fabrication PDK address were not able to get. Actually, now TSMC is providing a resistive RAM libraries, but I have to show me that I have to fabricate a device with them, then only they will provide a resistive RAM libraries. So we published, we have done that. Computer arithmetic, only cryptography and neuromorphic applications are pending for our in-memory computing process. So this is one of the in-memory computing process. Throughout the world, they are going. It will be there forever. So I will only give very brief introduction about quantum computing. Just now we have seen the quantum where we are position of the electrons, we are changing position, correct? But if you come into quantum, the state of the electron, so electron can rotate. Electron can rotate in three directions. Right? It can rotate in any direction. Like so let's assume that this kind of cross here or something. This is what will provide the state of the electron. You can measure the state of the electron. Actually, we can do wonders. That is the idea. where people want. The theory they have developed long. So the side function is what? It will give the position of the error. So now they got this idea and they are able to measure in which direction the error will. So you have you have to take one basis. So you want to use one basis for representing restars. You can take the Z basis or X or Y basis. Okay. When a qubit is in the state 1 and state 2, the measurement in Z basis always result in 0. And you can see that actually there are very, very few groups in the world they are working on this quantum. One is University of New South Wales, Australia. The group, Andrew Zula group, they are actually working on the quantum qubits. So there are many ways. One is called quantum trapped ions, superconducting transformer. So okay, I think IBM is working on the superconducting one. This qubits fabrication itself like a, you want to make a single qubit. Can you tell me how much money I need? Yes. If you want to fabricate a qubit, let's say how much money do you need? To set up a basic lab qubit fabrication, a single qubit, I need 1,000 crores. Now these are the quantum missions, whatever we have proposed governments of India. IISc Bangalore, they have fabricated qubits. There, I think that labs are not working, I didn't go much details. That lab, won't visit when you have a time or something. They have fabricated qubits, 6,000 crores, 6 clusters they get. 6,000 crores. To fabricate at least qubit, they would have done 1,000 crores to 2,000 crores. Okay, these technologies, these equipments are very, very difficult to get. And also, you fabricate it, you cannot operate them in the room temperature. You have to operate in the cryogenic temperatures. You know why you have to do higher studies? To go to these labs and to work on. Okay, anybody can earn money. Okay, if you are lucky, you can earn a few crores or something, 1,000 crores or something. And by the way, you are getting money. There is a one. Two first will go in. One guy says that I am working as a software something. What is your salary like that? That guy will ask. He says that my salary is like a 50,000 or something. Then that guy is per day I am earning like a 5,000 to 10,000. Salary, if you based on the character or salary, the tea, you make a tea and sell it. Okay, by this time you have made enough money than minimum. If the tea is good. Tea is bad, nobody will drink. Okay? And by the way, the journey where you are going to enter, the salaries will become, whatever basic wages are there, they will become high. High in the sense, more, now it is very, very low. And also now, how much do you think the card level is demanding? Let's say you want to come from Tirupati to Nellore. How much do you think that guy is charging you for driver? Minimum 1,000 rupees. From Lucky I can get 1,000. Let's say I want to go to Chennai, that guy will charge 1,500. If it is a Bangalore, he will charge 2,000. That is what I am telling. The base, like whatever loyal jobs, whichever that thing that is not well paid, when our economy becomes $10 billion, all the salaries, everything will increase for the base income. Okay. That is why you see there is a one guy he did PhD and then he is operating a fruits shop. Fruit shop. He is earning more money than whatever other faculties are doing. Okay. So don't measure your knowledge and thing with the salary or money. You will never be happy. Okay. So, Let's say if you in a classical computer, you send or throw some electron or something, it will be either of these one position, correct? But in a quantum computer, if you just throw some ball or something, it becomes like it can be in either of these, both the positions at the same time, it will be. That is the difference between the classical electrons and the qubit. So how do you measure it? Is using the superworm. You will only get the measurement of that. Okay. What is the probability of? If you measure what is the probability of electron being here, what is the probability of electron being here? If you measure different probabilities, you will get it. Okay. This is the one of the things about quantum. Okay. And you need to know about good basics of physics, classical physics, followed by quantum physics. Okay, then you will do very well in the quantum. Quantum entanglement is very nice phenomenon. You take any two qubits to separate them to, let's take to other side of the earth. Other side of the earth. If you take it, what will happen? If I change my state of here qubit to some state, the other side also will change automatically. So the state will automatically is called entanglement, and I didn't understand this phenomenon. They call the action of electrons or something. This is called entanglement. When you are making a qubit, entanglements are very important. Without entanglement, you make a qubit, nobody will appreciate. This has a very good properties. Currently, you want to establish a quantum key or something. This is how they will do. They will prepare a two states entangled, and then they will establish a key like this. If you try to measure what is the state of the entangled, both will get disturbed. And when you get disturbed the state, it will collapse. So you cannot get back the key. That is why it is very safe to use quantum key. Next. And here we have some gates different than the normal gates. Yes. Okay, this is the one of the XR gate, and also quantum gates are of the reversible gate is, for example, you take this outputs, okay, from the outputs you can get back the inputs. Whereas in the AND gate you give the two inputs, you will get back output, correct? From the output you will never able to get back the input. So in the quantum all the gates are reversible. From the output you can get back the input. So these are four gates, different gates they have made. Some of you are interested in the quantum computing. Any of you want to use any quantum computer? Which quantum computer you use? IBM will provide some free of cost. Even Google also provide up to 5 qubits or something. You can use for free of cost. There is a quantum inspired by University of Delft, Netherlands. They will provide free of cost to run your algorithm with their quantum machines. Actually, this is one of the full ladder. You can even arrange like this. Because how many inputs are there? Similar number of outputs. Okay. Usually, previously quantum computers are there. Okay, it's okay. It will do fast and all this. people are thinking that 1994 Peter showed that you have a quantum computer currently cryptographic keys, like I can break the cryptographic algorithms, key exchange algorithm. That is what he proposed. So that is where created a new kind of a computational paradigm. If the paper would not have been there, would not have published, people would not have taken serious about quantum computer. And also whatever normal time will take, exponential time takes in classic computer, will take normal time in quantum computer. So this is the one of the you can note down this paper, read about this paper. Peter Story. So from there people working on different different algorithms, and then they worried that if I get a quantum computer, whatever your bank passwords, whatever you are using, OTPs, they are no longer safe. So that's why people started looking into different cryptographic algorithms now onwards. Okay, if somebody makes 10,000 qubits, you can break your banking and our credit card, all these passwords you can break. They are very, very powerful because of this mathematics. So, but I will only give this basic idea what he found. Cryptography based on the modular arithmetic. You take a sequence of some numbers, okay? 2 power 1, 2 power like this. When you do mod 50 of the numbers 2 power, so usually you take 2 power, take mod 50, 2, 4, 8, 1. After that you can see the repetition of sequence. Similar. You take mod 21. Okay, you take like 2 power something. Again the sequence will repeat. Okay. So what is the source and then try to find at what power this is started repeating. Okay. If you find out this repetition using the algorithms, you can get back the what is the volatility between the two parts. Sort of I'm skipping. That was the idea about Peter. These are all takes only quantum. I can maybe after 6 months or 1 year. I don't have any students to work on this problem, so I'm not working on this quantum completely. But when we found some students or something, I can come and do a very good lecture on this, how to break these keys and this. Actually, the interesting idea is he finds some sequence and then he will apply to Fourier transform. When you apply Fourier transform, the periodicity, from that they will try to find a power R or something. So this is the, you can go, you have time in this algorithms. So public cryptography is dead. So what they have done, post-quantum cryptography, they made. I will tell you one. What is the time? Okay, let me give you secure communication. One of the areas is cryptography where I am working. I found out that it's very, very interesting during my post. Yes. So Bob want to send a message to some person. Alice. Okay. They wanted to both want to exchange a message. Then how do you think they will exchange a message? If you send a normal message, they will read it. Okay. So they what they will do, they will encrypt the message and they will send to others. And then she will decrypt the message and then she will read. Okay, that's how message is exchanged. But to do this message exchange, we needed some key agreement between them. So if you don't have a key here, you will not be able to get. But what happened is one called he always wanted to know what is the distance. So you cannot access message, but they will stay in insecure channel where they will get cybertext. It's called cybertext. From that you try to find the key or try to find the message. If you know if you get a key, it will get that. So that is how usually you get. So what will happen is if quantum computer comes, it will quantum computer, whatever this key is there between these two parties, it can know that the key. Because this key also has to be exchanged between these two. So this key exchange mechanism is called public key cryptography. Without that, we cannot perform any encryption, decryption or anything. Okay. So this is very, very interesting field. This itself we want to take a lot of time. So what we found is in a secure communication, let's say somehow I end up in this area, but it is very, very interesting. Let's say somebody wanted to send data from one place to another place. That data should be secure. Secure is confidentiality. And other thing is, they cannot, somebody what they will do, there is one more person, he will stand here, he will stand in between them, and he will try to read what is the information going on. You know, you can see some English movies, recently Telugu movies also, both of them they can have that traffic in correct. All the movies are many places, they will have the traffic in they will manipulate the information. When you manipulate the information, I should be able to identify. If I am not able to identify it, then there is no use of this. And also, secret key generation. How do you use some shared secret between them to find out it? To do the exchange. Can any of you tell me? Can you tell usually if you want your friend to want to exchange some messages? How do you exchange? Without knowing the third person? WhatsApp. Did any of you even look into that? This is one of the very, very interesting area. Cryptography. Even people are moving to AI and everything, correct? Even the AI also, it is neural network. If you change the weights, okay, whatever the matrix multiplication, the weights, if you change it, the output will change. All of you know about AI, deep neural network, those things. So how do you prevent the hacks also? There is one area. So this cryptography area is very interesting. You won't read. Actually, you can even create your own algorithms also. And it has a scope for research always is there. Let's say I have all these three things, but if I am not able to implement in my own hardware, it becomes a lot of money. That algorithm is useless. Okay. Now all the defense people, everybody uses this different type of security algorithms. Next. So usually when I wanted to say I have listened like that by reading many papers, usually key generation, tag encryption, decryption, authenticate modules are the essential modules to any circle. And you can do this one. Actually, you have this Arduino course. If some of you are interested in the project or something, you have one more year. Huh? You have one more year? 5 years. The 5 years, one more year is there. 4 months. Then 4 months. 4 months means they have December month. After that, they have up to May. Okay. You have 2 semesters, correct? So, very less cost. You buy something called Arduino boards or Raspberry Pi boards. Arduino boards, buy some camera, some Bluetooth or something. All these things are available. You just connect to internet or Wi-Fi, encrypt the message, and you receive in your computer. You try to decrypt this. That's not very difficult. It's easy to do. Or usually, Android programming. All of you know Android programming. Huh? You want to pick software engineers, you don't know Android programming. So then Android programming, it takes like 1 to 2 months or something, or 1 week to 2 weeks. What you can do is, you can create your own with this cryptography algorithms, and you take a picture, you send it to your friend or something. He has to use the same app to decrypt that image. And how do you stay a secret key? You can use some UPC algorithm, postman something to into the creation. Doing these projects are very interesting. They won't take much time also. But if you come into real time, one of my students have implemented this in Android. But I asked him to make real time, that became very simple. And what is happening is, there is a new cryptographic algorithm called authenticated encryption. So previously, algorithms used to do encryption, and authentication is do by different algorithms. The new set of algorithms, what they will do is, they will encrypt as well as that will provide a tag encryption. Some of you are interested in authenticated encryption. You can implement in pure vanilla. Pure vanilla. I can show you afternoon where to get these resources. Okay, what algorithms to be implemented. You implement in the hardware, then you can even produce a paper, better conference or journal papers also. It will be very effective. And you see, the guide thinking and researcher thinking, how it will be, that is why I always keep it physically unclonable functions. You know, it's the same thing. You ever wondered, one or two guys sitting back to back or side by side, both one guy will copy from the other guy. Okay? But sometimes what will happen, whoever is copying, he has copied as is from the other guy, the copied guy always gets more marks than the original. What happens? Why? No? Other than content, everything is the same, but the copied guy always ends up getting more marks. Whether it happened to me. There is one guy who goes to my intermediate or something. I don't like to copy also. That is some mental I got. There's one guy behind me or next to me. He always keep some crying face. If you don't know the answer or something, you always keep a crying face or something. The short question I know, I used to show you. The funny thing is that they got very huge marks. Like he is almost top 10 in the intermediate college. Almost he became that much level. Mine is like below 400 marks. So what? There are two things what happened. Whichever question he don't know, he is writing, he is asking me, and also there is the difference I asked, don't copied one. Usually copied people's handwriting is better than the normal ones. So that is what usually they will end up with. That's why don't show your answer to other guys. you will get more marks. Always it will happen. And what will happen is, this is called dye. You know what is called? This is a dye, silicon dye or something. You take one circuit of this, other circuit of this one, this dye, both of them are not. You will be different. Okay, like how two people handwriting is different kind of thing. This device is also very, very different. This idea, one PhD student from MIT he got. What he did is, why do you, when you want to generate a random number, it's very difficult. Random number generations, two random numbers we are not able to generate it, but his goal was to generate a random number. So what he found, you take these things, you cannot, they are not same, but how do you capture this randomness? How do you capture this differentiation? This is what he got when he had. Simple circuit he created. To capture this, one of the axes, he created a circuit. The same circuit he kept in a different, these circuits he fabricated like a 2 to 3 level. To capture this is called oscillator based one. They can use multiple number of gates. So what will happen is, if the delay, whatever this inverter will do, the delay of this one and this one is not equal, because we will have some nanosecond or a picosecond variation will come. That variation will make it like that. This frequency of this square wave, this one is completely different. If you can capture that difference, you will getting a good random signal. To capture that, they have given to multiplexers. Again, other details will come into picture, and from there they have taken 1 and 2 counter, and they have compared each other. This is how they have created a randomness circuit. They have fabricated. After huge research is happening in this physically unknowable function, now speaking based any device is fabricated, but it will be very, very different. So you just fabricate some random number like this, that will become a good paper or good patent also. So we have implemented this in FPGA. So we can discuss this. This is the entire algorithm which we have. This is the circuit, and you implement this using your Android or Arduino boards. Instead of that, this algorithm will just change. Thank you everyone. We will meet after.
Sir,